What happens when we try and balance that first one? What's our first step? We should be doing our same pattern that we've been doing all the way through. We want to try and balance each element. So zinc, there's 1 and 1 on each side. Hydrogen, there's 1 and 2. That doesn't balance, so I need to put a 2 in front of that hydrogen to make that a 2. Now what happens? It would look good. The last thing that we should do, which is what we talked about Tuesday, was we also need to balance charge. So when we look at the charge, what's the charge on the left-hand side of the equation?
Plus 2.
Every hydrogen is a plus 1, but there are 2 hydrogens. So the charge on the left is a plus 2. On the right, it's a plus 2. So what happened? Charge balanced. Okay. We now have our balanced equation for that one. Relatively straightforward and simple, following the same rules that we started with from the very get-go, and we didn't have to worry anything about the charge. What happens with the next one? Could look at the irons, 1, 1, tin, 1, 1. We'd say, well, the elements are balanced, but the charge on the left-hand side is plus 5, and the charge on the right-hand side plus 6. So the charge isn't balanced. We'd have to somehow balance it. Okay. How could we go through and balance it? We talked about a couple different ways. Yes?
And what are they called? The coefficients to different elements to try and balance.
So the official way is trying to add coefficients through, because the other way, which maybe hunters are going to suggest. Okay, Hunter's not going to suggest it quite yet. We could try and add electrons in to balance out the charge. Okay. So we could add in an electron on the right-hand side, and now what happens to the charge? It would balance, except electrons are inherently unstable and we can't have them ever exist in solution. Okay. So what Hunter suggested and what Chandler suggested are both getting at the same idea. We need to somehow change the coefficients on each of those metals to get it to balance out. Hunter was suggesting a methodology. Chandler was suggesting the end result. Okay? So we've got a couple options. When we talked about this in class, okay, if you remember from Tuesday, I kind of stared at it for a little bit with it all being blank, right? We had this weird awkward silence of me staring at it and then saying, I think this works.
You said like 2.
And if we tested that, what happens with our charge? On the left-hand side, we have a plus 2, plus 6, a plus 4, plus 4. Oh, I get plus 8, plus 8. And look at that, it worked. Okay. And you may have said, well, how the heck did you figure out that it was 2? Well, I had a rough idea, okay, but really I just guessed, threw it in there. Okay. The issue with guessing is maybe I'm not going to be right every single time. Okay, for instance, if we move to the next one down below, what happens when we go through and look at that one? To balance the copper, 1 and 1. To balance the nitrogen, 1 and 1. To balance the oxygen, what do we have for the oxygen? Well, 3 on the left and 3 on the right. To balance the hydrogen, 1 on the left, 2 on the right, so I need that 1 on the left become a 2. Be 2 hydrogen. And now if I went through to balance the charge, so I'm going to have to erase all that work because I can't write charge in there. What's the charge on the left-hand side? Plus 2 minus 1 gets me plus 1. And on the right-hand side, does my charge balance? No. So I again have this problem. Well, how do I fix that? Well, obviously, the way to balance it is I need 4 hydrogens, 2 nitrates, 2 nitrogen dioxides, and 2 waters. Right? Everybody's like, oh yeah, that totally works. Okay, obviously, yeah. Something isn't there. Okay? There was very unlikely that I could have just guessed at those numbers. We had to have a method and an organization behind it. Okay? We can't just guess. Guessing works sometimes, but not all the time. Okay? We need a methodology. We need an organization behind our writing. I mean the chemistry. for our solving process. Right? So what is our solving process? We need to observe. We need to look at the reaction. So we've got a reaction equation, and we'll do a quick analysis of that, a quick evaluation. Is it accurate? Is it balanced? And when we look at that equation, is it? Should remember, because it was just up there. No, it's not. So now we go through our analysis of this. We have to initiate the process of balancing it. Okay? That's looking at each of the individual elements. Okay? Once we think we've got it, we evaluate it again. Is it balanced? Which we did that evaluation. Throw that in here. Is it now balanced? Yeah. Was that an effective process? Okay. Did that get us our answer? Okay. What do you want when you are starting to work on a problem? What's your whole goal? Getting the correct answer. So is that an effective process? Yeah, that worked. Okay. What happens if we move to the next equation? Okay. We look at our balancing. Is it accurate? Is it balanced? No. We need to go through our process of balancing it. Okay. And then we'd have to evaluate again. Is it balanced? Okay. Well, the process that I used previously was I just guessed. Whoops. Wrong pen. Okay. Is that an effective process? Okay. You're saying yeah, because why? It got us the right answer. Okay, so let's use that.
What if you had guessed and started with the 10 instead? Like if you tried to balance based off the 10 instead.
You and I are going to be running on the same wavelength. The process that we're using must be repeatable. So if I'm guessing and saying the iron needs to be 2, okay, and it happened to work, great. But if my guess started at the 10 and it didn't work, what does that mean? My process was not good. Okay. The next level I was going to run at is trying to guess at balancing this one. Are we going to be able to guess and get this one balanced correctly in the first try? No. So what we want is a process, a way to approach and think about that problem so that we consistently get the answer right. Guessing works well if you're right. Okay. But what is your threshold for guessing and having it be okay? Are you okay if 50% of the time you're right?
No.
Okay, 60% of the time? Okay, where's your threshold?
80, 90.
Okay, I'm hearing 80, 90, 100%.
I mean, I want to.
Okay. If we're going to approach this, we want the highest percentage possible on our process. It needs to be as accurate as possible. Okay? So how do we go through and do that? That's what Hunter was suggesting when he was saying we should split it into the half reactions. The reason we know we have to go into half reactions was because of what? Say that again, Jessica? Oxidation and reduction. When did we start talking about oxidation and reduction?
Tuesday.
When we noticed we had a charge imbalance. So the only time we need to be concerned about dealing with oxidation and reduction and these half reactions that Hunter was talking about, okay, is if we have a charge imbalance. So when we go back to this question, did we have a charge imbalance? Okay. Yeah, we had a +5 versus a +6. Okay. Yeah, I could have luckily guessed at it, but I want to start my process on start my methodology on building a process with the easiest example. Because if I start working with a process or a difficult question on building my process, it's going to make life a lot more difficult for me to understand and follow through with. Okay, so let's start with this one. Okay, our process was to split this into half reactions. Okay, so what we want to do is take the parts that are similar on both sides and just look at those. So I want to look at just iron +3 becoming iron +2. Okay. Is that equation balanced? No. Why not? What's unbalanced about it? the charge. So what do I need to do? I need to add electrons. Where do I add the electron? Okay, the left side. I can check my work. What is the charge on the left-hand side? A +2, and on the right-hand side, also +2. So my charges balance out. Make sense? Okay, as was addressed on Tuesday, someone said, well, you can't put electrons into an equation. You're right. We can't use electrons in a balanced reaction equation. Is this officially a reaction?
No.
No. It cannot exist on its own. It must be combined with its sister reaction, its other half reaction. Why we call them half reactions. So what is the other half reaction that's occurring?
Tin, tin, obviously charge 2.
10 plus 2 must go to 10 plus 4. Okay, the charge isn't balanced in that one, so again we want to throw in electrons. Where should we place electrons? On the right side. If I place one electron in, is my reaction balanced? No, but I'm getting closer to it being balanced, so how many electrons do I need? 2. And now that bottom equation has the charge balanced. If I now want to look at the overall equation, what I now need to do is add those two equations up. Okay? And just like we would see in, say, an algebra expression, if I had, sorry, I had to come up with an algebra expression really quickly here. X plus y equals 2 plus y. What is x? X equals 2. Okay. Why can I remove the y from my expression? It shows up the same on both sides, so I can condense it. I can do the same thing with the electrons. Okay. The electrons show up on both sides, so I can condense them. And if I added these two equations up, what would I notice, or what would I have left over? Feel free to shout it out anytime. Plus. How many electrons would be left over? Only one electron, because I started with 1. So that one electron cancels with one of the two electrons on the product side. Okay. Now I'm in my overall reaction. What's the issue with being in the overall reaction? Can I have electrons? No. So that means I haven't balanced it correctly. I need to reevaluate my half reactions. And I need to adjust the coefficients in those half reactions such that the electrons equal the same on both sides of the equation. Okay. Can I make the 2 equal to 1 electron? I could divide everything by 2. Can I have half of a tin atom? No. So can I make the 2 electrons smaller? No. So what does that mean I need to do? Make the other electron bigger. I need an extra electron. To get that extra electron, it has to be consumed by something. What is it getting consumed by? Iron. So what I need to do is run that top reaction twice. So I will change the coefficients of everything in that top reaction by 2. Because that top reaction needs to cycle twice to consume those electrons. What happens when I now go through to balance or add those two equations up? How many iron 3s do I have on the reactant side? Tins? 1. Iron 2s on the product side? 2. Tin 4s? 1. And electrons? 0. Now I should check my work and verify that I did this properly. Do I have the same amount of irons on both sides? Do I have the same amount of tins? Does my charge balance? Yeah. Okay. So the methodology is breaking it down into the simplest chunks we can, 2 reactions, or half reactions, and working from there. So let's try it again, but with a more difficult question. Okay. Yes, Megan?
On the homework, it asked which ones were the oxidizing agents and the...
We'll address that in just a little bit. Okay. So attempt this now. Okay. Run through the steps, splitting it into the half reactions. If you've got a question, raise your hand. I'll come to you. I gave you the easy half reaction. What's the other half reaction? Seen a lot of people writing H plus. That's a reactant, fair enough. And H plus going to wherever hydrogen shows up on the right-hand side. So writing H2. Is H2 produced? No. H2O is produced. You can't change the reactant or your product. This is H plus going to H2O. What is the problem with now including that oxygen?
That by itself is an entire reaction.
That oxygen must be on the reactant side for this reaction to occur. Okay. Well, what species is going to be carrying that oxygen? Well, that's why we had the top equation. Which of our reactants had oxygen in it?
NO3.
NO3. So that means I have to also be including the NO3 here. But what's the problem with that?
Because then that's an entire reaction by itself.
Now what have I introduced? A nitrogen. Okay. Well, for this reaction to be balanced, then what needs to show up on the other side? Something with a nitrogen, and that's going to be our NO2. Okay. So we now have our half reaction. Sorry, that one's a little small. I'll give you another 30 seconds to see if you can't balance that out all the way. How many coppers on the left-hand side? How many coppers on the right-hand side? 1. What does that 2 mean? The charge, not the amount, it's the charge. Okay? So it's 1 copper on each side. What is the charge on the left-hand side? 0. Charge on the right-hand side? Plus 2. Is the charge balanced? What do you need to do? We need to add electrons to balance out the charge. Okay? And so one of the things I'm noticing a lot of people being afraid to do is, well, I don't know where to place the electrons. Well, if you don't know, there's really only 2 choices. Guess. Doesn't matter. Write it down and see what happens. Okay. What is the charge on the left-hand side? -1. What is the charge on the right-hand side? +2. Okay. So we're evaluating our guess. In our evaluation, did we get closer or further from neutralizing the charge? Further. What does that mean about my guess? I put it on the wrong side. So what do I need to do? Guess the other side and see what happens. What's the charge on the left-hand side? 0 and 1. Is it balanced? No. To get it balanced, I need a second electron. I now have that top equation balanced. Okay. The next thing I noticed students go through and do is when we move to the second equation. When we look at that, you go through and say, well, the charge is balanced. I don't need to add electrons. When do you check the charge? After you've balanced the elements. Are the elements balanced? No. You have to balance the elements first. In that balancing, you should notice that we need to have 2 H pluses. And now that equation should balance out. We have 2 hydrogens, 1 nitrogen, 3 oxygens. Everybody see that?
Yeah.
What is the charge on the left-hand side? We have a -1 from the nitrate. We have a +1 from the hydrogen, but there's 2 of them. The overall charge is +1. On the product side, 0. Do my charges balance? What do I need to do? Add electrons. Where do I add that electron? Or those electrons? We'll add it to the left-hand side. How many electrons do I need to balance it? Just 1. 1 electron will cancel out that +1 charge. I now have an overall 0 charge for that equation. And that half reaction is now balanced. To get to the overall reaction, what do I have to do? I would have to then add those 2 equations together. Okay? So everything on the reactant side adds up, everything on the product side adds up, and then if something shows up the same on both sides, I can cancel. What are we going to notice is going to be an issue with this? I'm going to be left over an extra electron. I can't have that. So what do I have to do? I need to have 2 electrons here. To make that 1 in front of the electron a 2, what do I have to do? I have to change the 1 to a 2. But by changing it to a 2, what am I doing? I'm multiplying it by 1, which then means the nitrate must be multiplied by 2, which then means the hydrogen must be multiplied by 2. So it becomes 4, which then means the water becomes 2, and the NO2 becomes 2. The whole equation all the way across. Now when I add it up, I should end up with the 4H plus 2 NO3 minus plus our copper goes to our copper plus 2 plus our 2 H2O plus 2 NO2. But when I add this down, don't I see copper first? Why did I not write copper first? I'm seeing some weird faces, so maybe this is obvious to you. So let me try it, ask that question a different way. 2 plus 3 equals? 3 plus 2?
5.
What am I referencing? Addition doesn't matter the order. I can change the order of those reactants between the plus signs. Completely irrelevant. Okay? We should go through and check once more how many coppers on each side. 1 and 1. What else we got? Nitrogen. Left-hand side is right-hand side. Okay. Oxygen on the left-hand side.
3.
Why are you telling me 3? Because you have the 3 next to the oxygen there, but there's 2 of them, so we get 6. And on the right-hand side, 6 again. 2 from our water and 4 from our nitrogen dioxide. Hydrogens. We have 4, and on the right-hand side, 4 our charge, which I can't fit underneath, plus 2 on the right. Oh, but I got a plus 4 on the left, minus the 2 from the nitrate. Everything balances out. Deep breath, not horrible. Okay? It just requires practice going through and working with it. Okay? So now for the real quiz. Identify the oxidation states in the following 2 equations, okay, which should be relatively easy because I told you to do this on Tuesday. And then balance that last reaction.
Find the oxidation state when there's 3 elements.
Take a look at that one. Since I'm seeing a lot of questions on that second question, let's go ahead and move through that one. Our oxidation states, let's solve them all out. What is the oxidation state for Mn? What is Mn? Manganese, good. What is the oxidation state for manganese in that question? It's plus 2. Why is that nice and easy? It's the same as the charge, so that's nice. Okay? So I'm going to skip over the hard one, because you can figure that out later on your own. I'm just kidding. We'll look at that in a second. What's the oxidation? I appreciate the requisite laughter. Oxidation state for the bismuth? It's a plus 3. The oxidation state in the next question, or the permanganate? That's a trickier question, isn't it? Because we need to specify the oxidation state for each of the elements, not for the compound. The oxidation state for oxygen is -2. What is the oxidation state for the permanganate? Well, there is 1 permanganate times its oxidation state. I don't know what that is yet. Plus 4 oxygens with an oxidation state of -2. This has to equal -1. I can rearrange and solve for x, and I get x equal to +7. What's the oxidation state for the sodium? A +1. So now to the tricky one in the middle. How do we solve that one? If we wrote out our equation, we have our first element, which was what? Sodium with an unknown oxidation state, plus our bismuth, there's one of them with unknown oxidation state, plus 3 oxygens with a -2 oxidation state, and this must all equal 0. Okay. Well, I have one equation and 2 unknowns. How can I possibly solve this? This is coming back to recognizing what kind of compound we have here. If we were to name this compound, where would we classify it? Okay. And as a big hint, it really has to do with that first element. Because that first element is classified as a metal. What kind of compounds have metals? Ionic. What happens when we have an ionic compound? It splits into the ions, and really what I'm looking at is sodium ion with what charge? A +1, and the bismuthate ion with a -1 charge. How do I know it's a -1? Technically don't have to memorize the bismuthate. The overall charge must equal 0, and I'm required to memorize sodium. What does that mean the oxidation state for the sodium is? X must equal +1, because I can now divide this into 2 subunits. I have 1 sodium times, come on pen, oxidation state of X equals +1. X equals +1. For the bismuthate, there's 1 bismuth times an unknown oxidation state plus 3 oxygens times their oxidation state of a -2. And that must equal 7? Oh, I see what you're saying. A -1 as the overall charge. When we solve for x, we get x equaling not 7, +5. Right? Okay? Kind of making sense? Since we've got that one up there with all of those charges, what happened to the oxygen through the course of the reaction? Did it gain or lose electrons? It stayed the same. So oxygen did nothing. Okay, what happened to the sodium? Stayed the same. So I don't care about the sodium either. Okay. What happened to the bismuth? Was that a +5 and it became +3? To go from a +5 to a +3, what happened? Okay. It had to gain 2 electrons. For those of you saying loss, remember your electrons are negatively charged. If you lose negative, you become more positive. Here we're becoming less positive.
Is that the whole Leo says Gerd thing?
That is the whole Leo says Gerd thing at the next level. We have gained 2 electrons. By gaining 2 electrons, we have done what? Gain electrons reduction. We can end that anytime.
Yeah, I don't know what happened.
You forgot to tell them what it
Okay, reduction. What does that mean it acted as? What kind of agent was it? It was an oxidizing agent. What happened to the other species? Okay, we'd be looking at, oh shoot, I erased it. That was convenient. What happened to the manganese? We went from a +2 to A +7. What happened to it? It lost electrons. Okay. Loss of electrons is Sorry, my computer freaked out. Oxidation, which then means it was the reducing agent. Stepwise, all the way through. A mess of work going to be scattered all over the place to figure out questions like this. You do need to move through and show all of that work. Okay? Or you get really lucky and guess. Okay. Anybody get to the last one? Did you balance it? What did you need to do to balance? What's that? Yeah.
2 aluminums, 3 coppers, and then 3 coppers and 2 aluminums.
How did you balance that? So one method is splitting it into the half reaction. Anybody try anything else? Or see anything else? I'm hoping you didn't, because I don't want you to see that. I want you to do the half reaction method. Okay. So then the next question is, how many electrons were transferred? Okay. If we look at the balanced equation, does it show any electrons? Nope. Okay. This is why I asked the question, how many electrons were transferred? Because how do you find out how many electrons were transferred? You have to look at your half reactions. How many electrons were involved in your half reactions? And because, Simon, I know you did it, what did you get? 6. 6 electrons were required to be used in that half reaction balancing. If you did not get that, check your work, go through, balance everything out, and verify that. Okay. The redox section is not anybody's favorite. Okay. So you're not alone in that. It just takes practice. Once you've got the practice, it should come relatively quickly. Okay. If you don't do the practice, it will take forever, and you're really just guessing. Questions? Okay. Well, now for something entirely different, but not really. We've got our next reaction type, the double replacement reactions. Okay. In a double replacement, we're exchanging ions. Okay. You are required to predict these. Okay. So if we went through and tried to work through the bottom one, I should have actually edited the slides here. Let's take a look at that bottom one. Aqueous sodium chloride, what does that translate into? Sodium is, chloride is, aqueous. Reacts with is not an arrow. It's a plus sign. Lithium, nitrate, aqueous, AQ. And the part that's missing from this, to produce, now I have an arrow. To produce what? See what you guys can come up with. Talk to the people around you. We'll give you a quick 30 seconds. I'm recording. We'll look at the first response, which is our official answer, and then we'll look at the second response, which is our unofficial answer. You should always write out the unofficial answer first. Okay. That said, I'm going to give you the official answer because I heard everybody jumping to the unofficial answer. What is the official answer? What is NR? No reaction. How many people wrote down no reaction? Ouch. Fair enough. Okay, no reaction means you consciously wrote out no reaction, not you just didn't write anything. Just wanted to clarify that. What was the unofficial answer? We get sodium combining with the nitrate, and we would get lithium combining with the chloride. Taken a step further, you are required to specify the phases on both of those species. How many of you wrote down the phase for both of those species? That's why you didn't get the official answer right. Okay, which is okay, we didn't talk about it. But you read about it in the textbook when you did your reading.
Yep.
Right? So let's take a look at what those two equations look like. The first equation actually comes out and does do a reaction. The second one, because we end up with two aqueous species here, is a no reaction. We know a double replacement occurs because we see a change in phase. How do we know we have a change in phase? Well, it says solid next to it. Okay, we have that S. But if we're required to supply it, how do we know it's a solid? Okay. Unfortunately, we don't inherently know that. Okay. What someone went through and did a long time ago is ran a reactions of hundreds or potentially thousands of these and said these were the things that produced solids and these were the things that did not. Those are known as your solubility rules. Your textbook has a big list of your solubility rules. Okay? If we use those rules, can we match the phases in our products? So let's take a look at barium chromate. We need to find barium or chromate in our list of rules. Okay? I heard rule 7, chromate. Okay? Chromate in rule number 7 refers back to here. Containing the following ions are generally considered insoluble. What does insoluble mean?
Will not dissolve.
Will not dissolve. It means solid. Cool. Okay. What's the issue with that rule? We have exceptions. Okay, so they're telling you that you also have to go back and look at rule 1. What does rule 1 tell you? Alkali metal ions and ammonium. Remember when we talked initially about the elements and their family names and all that fun stuff? And we said you should know the names of each of the families? This is kind of where it shows up. Where are your alkali metals?
Far left.
The first column. Is barium in the first column? Nope. So it's not an exception, which means it's a solid. How about potassium chloride? What rules apply to potassium chloride? Rule 1 right out of the gate applies because potassium is an alkali metal. Notice where rule 1 is located. It's located under the heading. The compounds containing that are generally soluble, which means the phase is aqueous. Do we see a rule about the chloride?
Is 4.
Okay, 4. What does the rule about chloride say? Halides are generally soluble. So both rules are telling us the same thing, that it's soluble. Okay. So you have to be referencing your solubility rules. Okay. Which then means when it comes to an exam, what do you need to know? Your solubility rules. I saw lots of people getting excited and mouthing some bad words. Okay. Because what does that mean? You'd have to have all your solubility rules memorized. I have never memorized my solubility rules. That said, I do want you to do better than me, and if you memorize them, you would probably do better than me as a chemist. The other thing is I think memorization is a bit of a waste of time for something like this. Okay? And I might supply some useful information on the front of every single exam, and if you take a look at exam 1, what will you find? Some solubility rules. You don't have to memorize them, you have to use them. Yes?
I was just, when you were talking about memorizing, I was going to say, we talked about ways that if you do have to memorize something, what are some ways that it might be effective, part of an effective process to do that? Because we talked about that, right? I'm sorry, that was really... we talked about trying to use metaphors of building systems.
Metaphors, yes.
Systems, so if you did want to try and memorize this, obviously your punchline was way better. It's on the front of the exam.
That said, there are a couple of these rules that I would argue are super important to memorize. Rule 1, super important. I would just spend the time to memorize Rule 1. I would also spend the time to memorize Rule 2 and 3. And for those of you saying 4, 5, 6, 7, no. 1, 2, 3, that's it. Those are the only 3 rules I would ever bother to memorize. Any ideas why?
It was the most common, because it involved the most common.
It's even better than the most common. Take a look at rule number 4. Rule number 5. 1, 2, 3 have no exceptions. They are always true. That's why I would spend the time to memorize it, because I will always be right if I've got that memorized. The other ones have exceptions, and if I don't know the exception, then knowing the rule is pretty useless. Kind of makes sense? Memorization is useful if you are always correct. If you're only some of the times correct, that's not very helpful. Okay. We got 2 more reactions to cover, our neutralization reactions. So there's our general form. What do our neutralization reactions kind of look like? They are acid and base reactions by definition, yes. Do they also look potentially suspiciously like? Or if we rewrote this, we could write it out as A, B, C, D. What do I end up with? C bound to B. Neutralization reactions are double replacement reactions. Why do we refer to them as their own special category? Okay. If you talk to anybody outside of this classroom and you said, here, drink this pitcher of acid, what are they going to say? Ha ha, no. Okay. But if you told them, drink this pitcher of dihydrogen monoxide, or this pitcher of water, they probably don't care. Why? We're trained from very young age that acids and bases are dangerous, right? And we are taught to avoid them. Are they all dangerous? No. Okay. Probably what you're drinking in your sodas is higher acidity than you would care to actually acknowledge.
Say that
Acid-base chemistry is a very old chemistry, so it carries its own name for a reaction. That's where we're getting the neutralizations from. So we've got another example here. I want you to go through and predict. So give me the products of the complete neutralization of sulfuric acid with potassium hydroxide. All I want are the products. I will tell you right now, it is probably easier to determine what the products are if you have the reactants present. Okay? Draw them out, talk to the people around you, make sure you got it. So with the reagents up, what are we going to produce as products? Potassium, potassium with sulfate and H2O. Did anybody get anything different? Okay. I would argue HOH is easier to see, but H2O is okay. Did anybody get anything different from that? What's that? So an interesting question popped up. Isn't it K2SO4? Why are you saying 2? Sulfate's a -2, potassium's a +1. It has to balance. You have to form a balanced product before you can continue on. You have to have K2SO4. Why did we not then write H2OH? Because wasn't it H2 in sulfuric acid? The 2 is present to balance sulfate. Is there a 2 present in H2O? No. Once we've gotten the correct products, then we could go through and balance the equation. Okay? So that's our general form for our neutralization reactions. The last reaction type before we'll end for the day is the combustion reaction. It's the reaction of an organic material. Minimally, this requires carbon and hydrogen with oxygen gas to produce carbon dioxide and water. Why is this kind of a neat reaction to have memorized? What are the products of a combustion reaction? CO2 and water. That's it. Every single time. You will always produce CO2 and water. The issue that you're going to find with combustion reactions is not so much predicting the products, but it's going to be balancing the equation. So with that, we'll give you an equation to try and balance over the weekend. Good luck with that. It is a bit of a challenge, potentially. See what you can come up with. And we'll start going back to the beginning sections of our textbook on Tuesday. So PSS section and chapter 2.